Okay, so this is our first lecture. Um, this is the first topic in MSM 111 Mathematics Method 1, and this is an introduction to the theory of sets. Like I said, the difference is not that uh, um, the difference is minimal. Like you are going to apply the same knowledge which you acquired in secondary. So the only difference will be that this type of set or what you're going to learn in here will be a bit advanced. Yeah, so we may begin and uh, what the outline of lecture one. You're going to define what sets are and the notations of sets, the types of sets, operations on sets, laws of sets of algebra, sets of numbers. So uh, in this video, I am going to lay to end on laws of sets of algebra. So let's start with the definition of a set. So in my previous video, I defined a set as a list or a collection of um a collection of members or objects which have something in common. And in this lecture slide, they have defined a set to be a list or collection of well-defined objects. So what do they mean when they say well-defined objects? They mean objects which have something in common, objects which can be defined using a short phrase or a single statement. So let me break this down again so that you may understand what I mean. Um, um, Objects which are well defined. For example, when I get a spoon, a fork, a knife, a cooking stick, those qualify to be called a set because I can define them using one word or a short phrase, which is uh, a set of kitchen utensils. If I get a car, if I get a boat, if I get a plane and a train, those qualify to be called a set because they are modes of transport. That is the common one common thing about them. Even though they don't um um like they use different mediums, or let me say the speed at which they move is different, but they are all mode of transport. They are modes of transport, and that's the common thing about them. If at all we get, for example, uh, a stick, and then we also get a bulb and a a what's this? Maybe a stone. There's nothing common between those three, so they don't qualify to be called a set. No wonder they are saying a set is a list or collection of well-defined objects. So those members of a set are what we call elements. Elements are members of a set, so they are called members or elements. So um, we go on to so sets are denoted by capital letters A, B, X, Y, and its elements are denoted by small letters. Typically, this is how we represent sets, and you are familiar with this representation even at secondary school. This is how we used to write or to represent sets. So in an element X, if an element X is in set A, we say that okay, they made a mistake here. It was supposed to be X. So let me just correct this. Yeah. So we write X is a member of A. So X is a member of A. This symbol here, which looks like E, this symbol here is what we call, oh, I don't know how it's called in Greek, but it represents is a member of. So X is a member of A, meaning A contains X, or X is contained in A. So that's what it means. That's what it means. So, or that X belongs to A. If X is not a member of A, that's how now we write this symbol. This symbol. So this is the symbol here. So that's what it means. So I'm trying to be a bit fast. I don't want this video to be so big, like it will be costly, like it will consume a lot of data. So methods of describing a set. We have how many? We have two methods of describing a set. We have two methods of describing a set. So a set is normally defined by either listing its element explicitly or by specifying a property that determines the elements of the set. Roster, listing, or tabular form is where you list all the elements explicitly. So for example, if you say set A contains a e I o u, which is a e I o u, that's listing method. But in rule method, where you are given a rule to say set A is a set of vowels, then you will know in your head, if you know what vowels are, then you will list. Or set B is a set of consonants. Set A is a set of numbers from 1 up to 10, just like that. So this is the second method of um, representing sets or describing sets. So you can say set B is X is an integer greater than 0. So if you know integers, then you write all integers which are greater than what? Than 0. So all positive integers, you write. So that's one way, or those are the two methods of representing sets. We have roster, listing, or tabular form, or row method, or set builder notation. So um we go on types of sets. So we have finite and infinite set. We have finite and infinite set. Okay, so these things are straightforward. For example, if say let x be set of let x be set of the days of the week. So you know that we have um um Monday, Tuesday, Wednesday, Thursday. So if you are able to count the number of elements in a set, then that set is finite or finite, depending on to two. If you are unable to count the number of elements in a set, then that set is infinite. Is infinite. Let me take you back a bit. If you see this set here, which has been described like set B is, set B is a set of all integers greater than 0 here. So you know that all positive integers. So this is an example of an infinite set because you cannot count how many numbers are above 0. The list will go on, like you just go on up to infinity, 1 2 3 4, until the world ends. You just be counting. Yeah, so this is an example of what of an infinite set. And then this one is a finite set. This one is a finite set. It's a finite set because you know that there are only five vowels, yes, on the alphabetical order. So this becomes a set A is a finite set B is an infinite set. So if you are able to count the number of elements that are contained in a set, then that set is a finite set. If you are unable to count the number of elements contained in a set, then that set becomes an infinite set. So I don't need to spend much time that, yeah. So we come to the cardinality of a set. Cardinality of a set. So cardinality of a set is just the number of elements in that set. So they can't ask you to find the cardinality of an infinite set because you cannot manage to count the number of sets in an infinite set. So if they ask for a cardinality, definitely you should know that they are talking about a finite set. So a cardinal number of a finite set, no wonder they've said a finite set. So this is just the number, the total number of elements in that set. So if you say set A has got how many? Set A has got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. So the N A, and this is the symbol of a cardinality. If you see something like this, they are asking you to find the number of elements in that set. Yeah, so that's it. And then in set B, we have two elements. So n, small letter n, open bracket, capital letter B is equal to 2. So that's how we denote cardinality. So we have empty now or void set. Empty now or void set. So a set which contains no element is called an empty or now or void set, and is denoted by these two symbols here. Okay. So this and this. So you can either use one of the two. An empty set is considered to be finite and a subset of every other set. So you understand about the subset as we go yonder. So an empty set is also a finite set. Why? Because you can manage to count, the zero elements. So yeah. Okay, so for example, we have an example here. Let A be equal to X, okay, such that X squared is equal to 4 is odd. So this is an empty set because there is no way you can have an odd number after squaring. There is no way you can square an odd number and then come up with an even number. So what are odd numbers? Numbers like uh, um, 3, 5, 2n minus 1 or 2n plus 1. So whenever you square an odd number, you come up with an odd number. You can't if you square 3, you come up with 9, which is also an odd number. If you square 5, you come up with 25, which is an odd number. If you square 7, 7 times 10, 7, you will come up with 49, which is an odd number. So there is no way you can square an odd number and come up with an even number. No wonder set A is an empty set. So let B be the set of people in the world who are older than 200 years. According to statistics, B is an empty set because the lifespan as we go yonder, the lifespan of human beings is gradually reducing. It was 100, and I'm sure it's no longer 100. Typically, when someone reaches 50, 60 there, it's by the grace of God. 70, it's rare. 80, it's rare. Yeah. So that's it. Okay, so what is a singleton set? Singleton set is a set containing only a single element, just one element, just one element. So as you can see, uh, set A is a singleton and B is not a singleton because it contains more than one element. Okay, so what is a subset and a superset? What is a subset and a superset? Okay, so let me just check. All right, so a set a set A is a subset of set B, or equivalently, B is a superset of A, written as A is a subset of B, or B is a superset of A. If every element of set A also belongs to set B. I'll say that again. If every element of set A also belongs to set B, that is, X is a member of A, implies that also X is a member of B. we also say that A is contained in B, or B contains A. So what this means is that we can have a set like this. So you can have A is equal to 1, 2, 3, 4, 5. Then set B can start as 0, 1, 2, 3, 4, 5, 6, 7. So it doesn't necessarily mean that since all the elements in A are also found in B, it doesn't necessarily mean that if all the even like or even the elements in B should also be found in A. No, set B might contain more elements than set A, but as long as all the elements in A are also found in B, then A is a subset of B, even though B contains elements which are not found in A. So that's what it means. So yeah, so we say X is a member of A also implies that X is also a member of B. We say that A is contained in B, or B contains A. So the negation A is a subset of A is written A is not a subset of B, or B is not a superset of A, and states that there X is a member of A such that X is not a member of B. Okay, so let's look at the example here. Let's look at the example. So consider the sets A 1, 2, 3, 4. I mean 1, 3, 5, 7. Then B 5, 10, 15. Okay, and C, X is the prime greater than 2. Okay, so that's 3, 5, 7. So C is a subset of A. C is a subset of A because C contains all the elements which are found in A, even though A does not contain all the elements which are found in C, because there is one which is in A and C, and one is not in C. On the other hand, B is not a subset of A because there is no um except 5, but because of 10, 15, 20, which are not in A, then B is not a subset of A. But even though 10 is a member of A, so that's what it means. So a set A can contain all the elements that are in B, even though B does not contain all the elements that are in A. So you say A is a subset of B. But if you start with B, you say B is a superset of A. That's what it means. Yeah. So don't be confused. So equal and equivalent sets. So two sets A and B are said to be equal, written with this symbol, equivalence. So equivalence like this. If every element of A is a member of B and every member of B is a member of A. Let me give an example. So if we say this is my set A, so set A is equal to A, B, C, D, E, F. Okay, we close. Then this is my set B. A, B, C, D, E, F. So you see that set A and set B contains the same elements. Then A, we say A is equivalent to B. So all the elements in A are also contained in B. So we say A is equal to B. Yeah, they are equal. Yeah, so if every element in A is a member of B and every element of B is a member of A, that is A and B contain exactly the same elements. So that is equality We are not talking about equivalence. Get me right? Let me repeat. A, we have A, B, C, D, and then B, we have, maybe they might not be in order. Let me say B, D, A, C. Because these are same elements, we say A and B are equal. Equal, not equivalent, equal. Now, we talk about equivalence. Two sets A and B are said to be equivalent if A and B contain the same number of elements, not necessarily exact. So an example here I can give is A contains 1, okay, 2, 3, 4, and maybe B contains A, B, C, D. Then you say A is equivalent. I mean, okay. Then you say A is equivalent to B. So let me echo that again. If A and B, if set A contains the same exact element, meaning the number and the type, same element as B, then we say A is equal to B. But if set A contains the same number of elements as B, then we say that they are equivalent. It doesn't matter whether set A contains numbers or letters, and then set B contains, even if set A contains numbers, set B contains letters, as long as the number of elements is the same in both set A and set B, then we say they are equivalent. But if the number and the type of elements contained in both set A and B is the same, then we say set A and set B are equal. So equivalence has to do with number only, but equality has to do with both number and type. Okay, so we have an example here. So set E246 is a subset of the set F624. So yeah, so okay, since each number 2, 4, and 6 belongs to F, then we say E is equal to F. Since every element found in E is also found in F, and the total number of elements in E is the total number of elements in F, then we say E is equal to F, or F is equal to E. So for sets of natural numbers, Z, integers, and Q of rational numbers, of real numbers, okay, we have N. Okay, natural numbers is a subset of integers, is a subset of rational numbers, subset of real numbers, a subset of complex numbers. So you will get to understand all these when we come to sets of numbers. Okay, but right now, yeah. Okay, so we go to proper sets. We check. Okay, I'll end it at 30 minutes. Okay, so proper set. Okay, so a set A is said to be a proper set if a set B of a set A is said to be a proper set of a set B if A is a subset of B, but there is at least one element in B that is not in A. Okay, so that is A is not equal to B. In this case, we sometimes write A is A. So don't get confused. What they are trying to say here is that for A to be called a proper set, so let's say A has got elements like 1, 2, 3, 4. Then B is equal to 1, 2, 3, 4, 5, 6. Then we say A is a proper set of B. Okay. Yeah, A is a proper set of B. Why? Because they are saying, what they're trying to say is set A is said to be a proper set, to be a proper subset of set B if A is a subset of B, but there is at least one element of B that is not in A. That is not in A. So it doesn't mean A has to be, the condition here is A has to be a subset of B. But for it to be called a proper subset of B, set A or set B has to contain at least one element that is not found in set A. Okay, so let's talk about disjoint. So disjoint set, two sets are called disjoint if they don't have any common element. That is, if A is not a subset of B and B is not a subset of A. So in other words, for you to understand, disjoint sets are sets that have no intersection. Yeah, for example, in a Venn diagram, such sets are represented like this. Like this. This is set A, then this is set B. Then you draw a Venn diagram like this. So these are disjoint sets because there is nothing common between them. If they had something common, we would have had something like this. Okay, so this is our set A, this is our set B here, this is our set A. So this region is where elements that are found both in set A and set B are found because they are common, they are shared. Yeah. So if sets are not common, they have nothing in common, we say they are disjoint sets. Okay. What is a universal set? So a set consisting of all possible elements which occurs under consideration is called a universal set. For example, we can have sets like this. Uh, um, let's say set A, set A. So a universal set doesn't have to have it's a set of sets. Yeah, it's a set of sets. So we have A, set A to be 1, 2, 3, 4, 5. Then set B, we have A, B, C, D, E. Then set C will have okay, let me just end here. So the universal set, which is denoted by E or U, oh my god, what have I done? Okay, so we have set A, which had A, B, C, D, E. Then set B will have 1, 2, 3, 4. So the universal set will be a combination of these two. So say universal set, which is usually denoted by Jesus. Okay. E or U would be a combination of these two. 1, 2, 3, 4, 5. Oh, we don't have 5. A, A, B, C, D, E. So this becomes our universal. So in short, the universal is a set of sets. So all sets are subsets of the universal set, meaning all sets are contained in, or let me say, all sets are proper subsets of the universal sets because all sets are contained in the universal set. Yeah, yeah. Okay, so I'm ending it at 30 minutes, and I'll be able to okay.